Hello, everybody. Can you hear me okay? So, for those of you who don't know me, which I'm sure is quite a few of you, I am Sam Morrell, and I am the president of SpaceX, which is the society that has set this fine event up today. And everyone has done a fantastic job, if I do say so myself. So, Matt and I, who's the project coordinator for the society, will be talking a little bit about what the society is, what we do, and a load of the projects that we're currently working on, right?
Yeah.
So, before I let Matt loose with the projects, I'm just going to talk briefly about what the society is and how it came to be. So, what is SpaceX? What is our DNA, as it were? Well, first off, the somewhat boring answer is that we are a Students' Guild society at the University of Exeter. But importantly, we are dedicated to bringing people together through astronomy and space science, and that is one of our driving goals as a society. We are essentially, this year at very least, have been a hub to pull together a load of different people from different disciplines to actually collaborate on a really, really large variety of really cool space science and astronomy projects, and you'll hear about those in just a minute. But also, one thing that's very important to us, one of our core values, is that we also are driving and committed to doing outreach events in the Southwest. So, for example, this week alone has been really, really busy for us. So today is pretty much our biggest outreach event of the year. A lot of organisation went into today. On Friday, we went down to Cornwall to do a stargazing event with Carradon Observatory, and Mike will be talking about Carradon in a little bit. And on Thursday, we were actually in colleges, weren't we?
Yeah.
Doing outreach events to colleges in Exeter. So we have a really wide variety of things that we do, but essentially outreach projects and really just encouraging space science. And these are just a list of the projects that we're working on. I will tease you with 4 of them, but I'll explain the top one. Because xrt-c is actually really vital to the history of this project. So xrt-c is called Exeter Radio Telescope at Carradon. And essentially, it is a student-led effort to build a research-grade telescope for less than £10,000. And the idea behind this was to be able to conduct scientific observations at 21 centimetre, which is a very, very special wavelength for radio astronomers. It's the emission wavelength of neutral hydrogen, which is just all around the galaxy. And what we've been doing throughout this entire project is to actually develop and build an outreach program and to leave behind it a legacy radio telescope that can be used by members of UK SEDS, the UK Students for the Exploration and Development of Space, by amateur astronomers and education as well. So the idea is that all of those people will have access to observations which are usually tens of thousands or millions of pounds to actually get. So if you want a really, really comprehensive history of xrt-c, go and look at the talk last year because it was nauseatingly detailed. This year, we'll just go through the key points in its history. So first off, 2010, actually, it was conceived at the Norman Lockyer Observatory. The idea of building a radio telescope was conceived at the NLO, or history tells us that's what happened. But for a variety of reasons, that just never happened. So in 2012, we actually moved to the University of Exeter, and a similar project was run under the UK SEDS banner. In 2014, we managed to finally find a location, which is, of course, Carradon Observatory, which is where you see it being built here. This is the observatory domes, and that's the dish being actually mounted on the telescope on the day. It was a real problem trying to find a location, so we were very grateful to actually find Carradon. So, of course, this dish was mounted here in 2016, and then in 2017, we finally got the antenna fitted, all of the electronics sorted, and achieved first light. And then on the same day, it rapidly broke. So what we have is this fantastic first light observation here. This was taken, you can see, 2017, and this is a neutral hydrogen observation of the grass on the hill opposite the telescope because we couldn't move the dish at all. So thus begins the era of xrt-c I like to call the era of technical issues. So for the last 2 years, We've effectively been fighting back against a load of technical issues that have been trying to derail the project. But because we have such a dedicated team here in Exeter, and we've got loads of support from Carradine and Cornwall, we've actually been able to fight back most of those, and we're very, very close to actually getting this thing working. Which is the same thing I said last year at this conference as well. So take it with a pinch of salt if you'd like. So that's essentially the history of xrt-c. And where SpaceX comes into this is actually right around the 2014 area here. So the idea behind SpaceX was that it was founded to actually run this project for the long term. And along the way, we've also built up a load of other interests and a load of other projects that I'm going to hand over to Matt to tell you about right now.
Just make sure I got this right. Hey, my official title is Project Co-ordinator, and that basically means I just oversee all the projects that we're going over, and I talk to all the members who are interested in doing different projects, and I'm the point person between the members and the committee themselves. So I've gotten a good cursory knowledge of what we've been able to do in the society, and hopefully build up our society even bigger. Right, so our second longest project is the high altitude balloon. Now, the reason why I say the second longest is because we've also had an era of technical issues. Now, the high altitude balloon originally had the aim to build a payload, so a box of equipment that basically does different kinds of measurements in terms of the atmosphere, and send it straight up to the atmosphere around in the region called the stratosphere, so around 30,000 meters. Our aim is to fill the payload with a small computer called a Raspberry Pi, and take measurements such as temperature, and also what we've been mainly wanting to do is to look at the CO2 abundance profile throughout the atmosphere. The reason why that's important, for many reasons, is because you want to find out the amount of CO2 that's in the atmosphere for global warming reasons, for climate change, and we can actually compare data to Met Office data because they've been able to collect a lot of CO2 abundance throughout the years. So we want to actually, essentially a proof of concept that we can create a scientific payload and do some science as a student-run society. And also, we'd like to safely land it without hitting anyone on the head. This is Sam, who's kindly volunteered to test the impact forces of the payload itself. It was empty, I promise.
Wasn't that bad?
But the HAB has been, as I said, the second longest project because we've had a lot of technical issues. The reason a lot to do with it is because, one, we are in the southwest. So the only direction we can actually launch the HAB, the weather balloon, is in the northwesterly direction because either you'll hit the sea, the Bristol Channel, or Wales, and you have to go through a border to get to there. So it's kind of hard to actually get to the balloon if it lands anywhere else. In the northwesterly direction, there's Exeter Airport. The airspace, especially in the UK, the laws are very important to be able to obviously not break, and we have to get some permission to do that. So we actually have to send technical reports about a month ahead in time. The problem is, even with the best weather models, we don't actually know what the weather's going to be like a month ahead of time, and we're in England, so the weather always tends to be permitting. So the launches have always been a bit delayed, and sometimes there's always been a bit of technical issues. Main thing is the CO2 sensor. But we've made massive strides in the past few months, especially thanks to our General Secretary, Jack Dew, and another SpaceX member, our resident computer scientist, George, who've been working on actually looking at the code that the CO2 machine actually runs in, how it takes in the data and how we can get the computer to read it. And that's our General Secretary also soldering on some pins onto it so we can actually read the data from it. And we're actually very close. We're at the stage now just tweaking the CO2 project. So we're hoping to launch soon. And the only thing we have to worry about is essentially getting the weather sorted and getting permission from the airspace. But we're hopefully making this done really quickly. And in the future, to also progress and have more projects like this, do more complex measurements. So the next project is a new one for this year, Rocketry. We've always been interested in doing solid rocket boosters, so not any of the water bottle rockets you do in school, but actually have a model rocket and launch it up. Nothing wrong with that, but this will actually be really interesting. The main aim, we thought it would be a good idea to have an actual goal to reach. So rather than build a rocket, we actually entered ourselves into a competition to build a rocket. So the UK sets as an annual National Rocketry Championship every single year, and we decided to have the SpaceX group and team to design, build a rocket themselves, and be part of this process. And we're hoping to make this an annual thing every single year. And that is something that we want to have, have a constant project, because you can learn so much to do with the computing of it. So there's two sides. There's the electronic side, which is where you're actually looking at the telemetry, so how high it's going, and to actually look at the mechanical side, to actually modeling the drag coming off the cone to actually build the best shape we can get and to get the highest point. Because there's only one goal in the UK STED Rocketry competition. It's to reach the greatest apogee possible, i.e. the highest it can go. So this is an old design, but one design that we thought of was a two-stage design. So we had the top half, which we called the dart, and we had the second half, which had the motor. The idea was if you actually, at the end of the motor casing being used, you have the second half to completely eject, because it's just dead weight anyway. You can actually reduce drag as well, and therefore you can actually increase the upper stage by almost double the amount. Unfortunately, 1.2 kilometers, the amount of acceleration and g-forces at this height would just crumple the rocket. And we've actually found the electronic payload that we're interested in using, so we're actually wanting to do temperature and pressure data as well. You can't get the payload small enough to be able to do this two-stage design. But this is the brilliance of the project, and hopefully the next projects to come. We can actually come up with different ideas and have different people in the groups to come up with, just have different experiences in soldering, computing, and manufacturing. So if you always come up with ideas with different designs, there's always an opportunity to be able to work on it, which is why I think this is a very valuable project. All right, we also want to beat the actual SpaceX their own game eventually. So this is also a new project, and it's initially you might think, oh, is it astro-related project? Well, it does eventually go into it. This is the long-term idea. But the idea is, we've heard graphene for about the past 10 years is this magic new material. Frankly, I haven't seen anyone actually do anything with it. But we've actually got a good project idea, which came up with one of our members called Awa, and she's worked on graphene before. So the idea was actually create graphene and to embed it onto actual membrane, and we can actually use this as a water filtration system. The benefits of graphene is that it's lightweight, and in theory, if we investigate cheap methods to manufacture it, we can possibly come up with ideas to create cheap water filters compared to other water filters you see nowadays, like activated charcoal. So how this project essentially works is we're in the metamaterials lab. We have to learn to create graphene, and you can create it through several methods. You might have heard the method where you get essentially a pencil and some tape. Similar to that, because what graphene is just multiple layers of this structure you see in the background, hexagonal. It's just multiple layers, and that's what graphite is. Graphene is a single layer, or multiple thereof, up to about 10. And the idea is you can actually slide the layers off each other through shear forces and actually rip them apart and create the layers. So what we do is, essentially, it's called exfoliation. It's a fancy blender with some soap and water. What that does is it blends up the graphite, give you several layers of graphene, and then you pump it through a vacuum onto a type of filter, which is using Teflon. And then you can transfer onto any surface you want using isopropanol, a form of alcohol, because it evaporates through the layers. The problem is Teflon is very, very expensive. So if we want to investigate cheap alternative and methods to be able to produce graphene as a water filtration system, we have to find another material. So currently our team has been working on using fibers instead, so such as nylon or other type of plastics which aren't as harmful to the environment and which aren't as expensive to make. And also the whole point of this is a very new project. None of us have actually got any experience in any of graphene production before. We want to get trained in different forms of microscopy. So once you've made the graphene, you have to try and figure out, have I actually made graphene before? Because you could just be making, have you blended it up enough? Is it still graphite? Have you actually done what the aim was? So this gives a great opportunity for students to get involved in different types of detection methods to tell if you've actually got graphene. And the main goal is test water filtration, go to Mars. So what I mean by that is we've also joined another competition. It's called a Mars Colony Competition. It's about a 20-page report which we look at the economics, the science behind actually running a colony on Mars. And our main angle is going to be water filtration. It's one of the most important abundances you require for life. Humans can survive a few weeks without food, but they can only survive a few days without water. It's very important. And we can't transfer water from planet to planet. It's just outright impossible. So it's very important to be able to use something like water filtration to be able to run a colony. So this has been our aim to work towards, to create this report and do some actual science in our lab and use that as our main crux of the report. So we can actually filter through water, through the graphene, some dirty water, and we can actually get some clean from it, and we can show this is a viable method. And we've actually got some results in the most recent few weeks. Now, apologies, this is a picture of a figure, but this is using something called Raman spectroscopy. The only thing you have to know is that there's these two peaks. One of them is called the G peak, one of them is a 2D peak. Now, or did I get that wrong? Let's see. G peak and that's 2D peak. Now, if you've got a lot of graphene, that one's supposed to be higher than that peak. If you've got a lot of graphite, that one's higher. So that wasn't a very good sample. But we are learning to be able to create graphene more efficiently and using better methods. So hopefully we can actually see these swapped and we can actually see that we've created graphene quite nicely. This was our first attempt of graphene onto nylon. Nylon is very difficult to be able to transfer graphene onto, as we found out. But no one, as far as I've been told, no one's actually been able to transfer graphene onto nylon yet. So if our team is able to actually do that, this could be a really good step in terms of that science. Yep. So then the last of our projects I'll quickly go through is the TTT, the tabletop telescope. So as you've seen outside, that's an example someone's done online before. His name was Derpy. And we've basically laser cut frame, box, and gears for our telescope. Now this project was basically to create a radio telescope like the one at xrt-c, but one that can detect Wi-Fi signals. It's able to allow the public to engage with how non-optical telescopes work, which we can't move the radio telescope at Carrigan, people necessarily can't visit it. So this gives us a good example to teach people how these things work. And the whole point of building this is to have an outreach tool to be able to give to people. If you've got any questions about it, I'm more than happy to answer questions afterwards, but I'll pass it to Sam to be able to tell us about the future of the xrt-c.
There it is.
There you go.
And it's outside, I believe.
Yeah, it is outside.
Okay. So thanks, Matt. So that's kind of a summary of all of the projects that are going on at the moment and where they're kind of heading to. Yeah. But we left one kind of dangling. We left xrt-c kind of dangling. Now, assuming it doesn't get blown away by the Cornish weather, or we all just get sick of it and ignore it, what is it going to do? What's the future of the project? Well, the future, believe it or not, is actually quite bright. So, have you seen this before? Galactic rotation curve. So, what you actually do with a radio telescope is you actually manage to see material that's not being lit up by stars. Neutral hydrogen just floating in space is always constantly emitting these radio signals. So what we do is we can actually point the telescope at the galaxy and get not only where all of the material is in the galaxy, but we can also see what speed it's coming towards or away from us. And that's absolutely fascinating, because this is a long-standing problem in astrophysics. So if you have, say, a planetary system where most of the material is focused in the middle, say with the star, what you have is things that are closer to the star tending to go very, very fast, orbiting around very fast, and then as you go outwards away from the mass, they tend to get slower. So that's what's happening in this situation here. So you see, things in the middle are going around very, very fast, and then as you get further out, things are much, much slower. And that's what this curve is doing here. But the fascinating thing is that if you look at our own galaxy, the Milky Way, it's not like that. What you end up with is, as you go further out, the velocity stays more or less constant once you get past the middle. And you end up with this very odd curve here, which is completely counterintuitive. You do not expect to see that. And one of the things that has actually been used to describe this is, I'm sure everyone's heard of this, dark matter. Yeah? Heard of dark matter? Yeah, I thought a lot of you would have done. So the way that you describe this is dark matter. But what we want to do is actually measure this for ourselves, measure this curve for ourselves using our telescope. So what we can do is we can do many, many different pointings, so point at many different parts of the galaxy until we build up a map that looks a little bit like this. This is one from a very, very expensive telescope facility that's got a much better telescope, basically. And what we can do is we can measure the galactic plane, look at the speeds, and then we can balance the force that gravity is pulling into the middle of the galaxy against the force, the centrifugal force, which is trying to push all this material out. So we can balance those two forces together, and not only can we look at this curve, but we can also measure the weight of the Milky Way. So that's one of the immediate plans for this telescope, is that we want to do a survey which actually measures the weight of our own One of the main limitations of our telescope is actually its resolution. If you look, say, through a normal optical telescope, you can see stars really, really well. They may be a little bit blurry on the smaller ones, but you can see them very well. On a radio telescope, you actually end up with a very, very blurry image. So you can't end up making anything out that's smaller than the full moon, for example. But there is one way around this, and it's a technique called very long baseline interferometry. And what this lets you do is actually take a load of radio telescopes, often quite far apart, and actually add them together and make a virtual telescope that is much larger than the individual ones together. So they can be tens to hundreds of miles apart, for example. So what we have here is an example of the UK interferometry network called eMerlin. And eMerlin is a very good example of this. So you can see there's those radio telescopes placed all around the Midlands and the north of the UK. And what they're doing is simulating like a 100-mile wide radio telescope. But you see, the interesting thing is that takes a lot of money to actually get time on that network. You have to have a very good research grant. You have to have money to actually get observations. So what we've been thinking for quite a while is, what if we could get a load of amateurs together from across the country, and we could build our own network of these telescopes? And there's a few technical challenges to actually get over, mainly in timing, the accuracy of the timing, that kind of thing, but it's a completely feasible opportunity. So if anybody knows anybody who might be interested in maybe setting up one, it's kind of on the roadmap for the project when we get it working and we've got it. It's a potential project. And I bring this up, eMerlin here, not because it's a UK network, but because the Southwest is actually making a good contribution to it. And Goonhilly, which is right down here on the Lizard in Cornwall, whose CEO actually came and did a talk for us in this conference last year, Ian Jones, is actually adding one of the telescopes to this network sometime soon. So you'll go from the longest baseline in this network being somewhere around here to the longest baseline being this one here, thanks to something that the Southwest is bringing to this space science industry. So as well as all of the satellite applications, the satellite communications that Goonhilly is bringing, they're also bringing a lot to astronomy as well. So I think that more or less covers. Thanks to listening to both of us, and if you have any questions, please feel free.